why the stationary distribution is either minus f. But if we look at how this Langevin dynamics corresponds to the evolution of the density in the space of distributions, then we have this result saying that if xt follows this Langevin dynamics, then the distribution rho t follows a PDE, this Fokker-Planck equation. So this is just a translation. But then, interestingly, this Fokker-Planck equation can be equivalently written in the following way. And we see that there is this the gradient of the log relative density that comes up explicitly here. And this shows why mu is stationary, and this is a good dynamics for sampling from the target. But in fact, more than that, this dynamics is nice because it's actually contracting. And so no matter where we start, we always get closer to the target. So one way to see that, for example, is to say that along the Langevin dynamics, we have the following identity that's called the Bruin's identity or the energy identity, which says that if we differentiate the KL divergence between our current iterate rho t with respect to the target nu, then the time derivative is something that's called the negative Fisher information, and Fisher information is always positive, so this time derivative is always negative, so the KL divergence is always decreasing to the target, which is very nice. And then if we have more assumptions on the target, then we can prove convergence rates, right? So in particular, here are some nice conditions. So we say that the target nu is strongly log concave if f, the negative log density, is a strongly convex function. So it looks like a Gaussian basically. Or the target satisfies log-Sobolev inequality if for any distribution rho, this Fisher information is an upper bound to KL divergence. Right. And what is true is that this is a weaker condition because strong log concavity always implies log-Sobolev, but log-Sobolev, sorry, there is an image here that doesn't show up. It holds a lot more generally because log-Sobolev inequality is stable under bounded perturbation, Lipschitz mapping, and some other operations also. Whereas log concavity like this is very brittle, right? We perturb it a little bit and then we get some like weakling thing here. It becomes non-log concave. So then, still in continuous time, if we know the target is log concave, for example, weakly log concave, then in fact we can show that the KL divergence decays at a rate of 1/t. Whereas if the target satisfies log-Sobolev inequality, then it decreases exponentially fast, where alpha is the constant in the log-Sobolev. And in fact, on the log-Sobolev, it's also true that the Rényi divergence is also decaying exponentially fast for all order Q. And I don't have the definition here, but this is a generalization of KL divergence. So KL is the case when Q approaches 1. Right? So in fact, condition at log-Sobolev is very nice because it allows us to say this very strong convergence guarantees for Langevin. And interestingly, there is also a natural way to view Langevin from the optimization perspective, because this Fokker-Planck equation, which is the Langevin dynamics in the space of distributions, is actually the gradient flow in the space of distribution for minimizing an objective function, which is the KL divergence. And this gradient flow happens in the Wasserstein metric, right? Because then in that case, we have these formal rules that tells us how to compute the gradient of some objective function. And if you apply that rule here, you get exactly the Fokker-Planck equation. Right? So this was the beautiful result by Jordan, Kinderleher, and Otto. And yeah, so for me, like this really explains why Langevin dynamics is the right, like the natural dynamics to use for sampling, because we are just doing gradient flow to minimize KL divergence. And what's also nice is that under this framework, geometric properties of the target distribution can be translated to optimization guarantees, to structural properties of the KL divergence, which allow for optimization guarantees. So for example, the target is strongly log concave is equivalent to saying that this objective function is a strongly convex function on the manifold, geodesically strongly convex, and therefore we know that optimization gradient flow converges very fast. And log-Sobolev inequality corresponds to a weaker condition called gradient dominated, or this PL inequality, Polyaklo-Jasiewicz, which we know, which from optimization, we know this is the weakest condition that we need to make sure that this objective function decays exponentially fast. And so all these geometric properties correspond to really nice optimization milling. So a simple example of the Langevin dynamics is this Ornstein-Uhlenbeck process, which is the case when the target is a Gaussian, standard Gaussian, let's say. So the score function is linear, and then the Langevin dynamics becomes a linear SDE, and this we know how to solve explicitly at each time t in terms of this weighted Brownian integral. Or if we only care about a specific time t, then we know that in distribution, it has this form where we rescale the initial random variable x0 by this exponentially small quantity. And then we also add an independent Gaussian noise with a correct covariance. Right? And either from this or also as an application of what we saw on the previous slide, we know that this is very nice. This converges exponentially fast to the target, which is, in this case here is Gaussian. That we know that starting from any rho 0, the Gaussian divergence goes to 0 exponentially fast with a rate of e to the minus 2t, and there is no constant here. That 2t because this Gaussian is one strongly log concave. Right? So for any rho 0, we have this fast convergence. Okay, and this is what we will use in diffusion model also. But as a side remark, so all of these results so far are still in continuous time, where we say that if we can actually simulate the SDE, the Langevin dynamics, then this is the rate that we get. But in practice, we have to implement that via either discretizing time or implementing the process somehow. So one easy implementation is this algorithm called the unadjusted Langevin algorithm, which has also been mentioned in the previous talks. So this is now a discrete time iteration. We maintain an iterate xk, which is a random variable. And then we take a step along the negative gradient of f. This is the score function with some positive step size eta. And then we add an independent Gaussian noise with a correct covariance. And we can see that as eta goes to 0, this recovers the gradient flow for this score function, and this recovers the Brownian motion. So this is consistent in the limit as eta goes to 0. But it turns out that for any fixed step size eta, if we keep running this algorithm, so this is a Markov chain, right? And this xk has some distribution rho k, and that rho k will converge to a limit, which is not the correct limit, not the correct target mu. In discrete time, these random variables will converge to some other distribution, a biased limit, and that biased limit will be different from the true limit for any positive step size. And this is not just an artifact of the analysis, because this actually happens even for Gaussian target. And the issue is that then that bias limit becomes the bottleneck if we want to analyze the iteration complexity. So what we can say, for example, is that accepting that there is bias, we can prove bias convergence guarantee. I think in the previous talk, we've seen a similar guarantee in W2 distance under a strong log concavity. If we only assume log Sobolev, for example, so we don't have convexity, we cannot do coupling techniques. Under log Sobolev, and if we assume that the target is smooth, meaning that this F has bounded Hessian, then for small enough step size, the KL divergence at the kth iterate is bounded by one term that goes to 0 exponentially fast with k. So this is like in continuous time. But then plus this asymptotic term, which doesn't go to 0 with k. This is independent of k, but it scales with the step size eta. So even though there is this asymptotic term here, we can make this small by choosing eta to be very small, right? So this means that what is the iteration complexity for ULA? If we want to make sure that we want to get an error, say epsilon for the KL, then we can choose eta and k so that this upper bound is less than epsilon. Right? So that means let's choose eta to fetch size on the order of epsilon, the error. And then we need to run for this k number of iterations. And in the end, what we'll get is that the iteration complexity to get error epsilon is something like this. Dimension times condition number squared. This is this kappa is L over alpha. But then there is this 1 over epsilon dependence on the error parameter. And this 1 over epsilon is actually problematic because in continuous time, we have exponentially fast convergence. So really the correct rate to expect is log 1 over epsilon. Right? And we know how to do that in optimization for gradient descent, for example. And yeah, and surprisingly for this basic algorithm, we don't have that. Now in practice, there are many ways we can address this bias, we can add this accept reject step metropolis filter that gives us MALA, the metropolis adjusted Langevin algorithm. It's unbiased by design, and we can show, or people have shown guarantees, for example, in TV distance, but using techniques that are currently still completely different from this kind of optimization-based analysis, because the technique there goes via Ordish conductance proof. And so this is a simple discretization that's biased. And let me mention also, recently there is another algorithm that some people call the proximal sampling algorithm. So this was proposed in some previous work, also by Lipschitz and Tian at fault 4 years ago now. And the algorithm looks like the following. So we want to sample from e to the minus f. We're at iterate xk. From xk, let's add a small Gaussian, so independent Gaussian with covariance eta. And then once we have this point, we want to sample the next point, xk plus 1, from a distribution whose density is proportional to this exponential. So we should normalize here over x. There is proportionality over x here. Right? So this looks strange. This looks somewhat proximal because this is a quantity that appears in the proximal method for optimization. And where this comes from, actually, this was introduced as this algorithm is really just doing Gibbs sampling for a joint distribution on this XY space. And what's nice about this joint distribution is that if we marginalize over y, if we integrate over y, then we lose this term, and then we get the x marginal, which is the correct target. So if we can sample from this joint, then we can just drop the y part, and then we get an exact sample from e to the minus f, right? And also, in a recent work with some colleagues at Cole 2 years ago, we showed that in a precise sense, we can actually view this as approximate proximal discretization of the Langevin dynamics, either using entropy regularization or via a slightly different perspective. And using that, we can actually show that this has, not only is this unbiased, but it has the matching exponential convergence guarantee. So for example, just assuming that the target satisfies log Sobolev without smoothness, assuming you can compute this update, then we can show that the KL divergence at the kth iterate actually goes down exponentially fast with k, with no bias term here, right? And then this implies that if we want to make this less than epsilon, then it's enough to choose log 1 over epsilon iterations, which is nice and matches with the continuous time guarantee. And this guarantee also works for Ragni divergence, for chi-squared, under Poincare, log concavity, and so on. So and also, like as a preview for the diffusion model, some of you might recognize that in a sense this actually looks very similar, very close to diffusion model. And in turns out the analysis was also very similar in hindsight. But if I have time, I'll go back to that.
Let me understand that. So in order to do that step, you have to do the normalizing or whatever constant you have.
Yeah. Yes.
The high dimensional
yes.
setting, you have to pay a lot.
I hit that slide that talks about that. But so one thing we can do this is that assume that f is smooth, so has bounded Hessian. And if eta is small enough, then this is actually a strongly log concave and smooth target distribution. And the condition number is a constant. So what we proposed, and also what was proposed in the previous work, was that we can do this by rejection sampling, for example. Because in D dimension, the complexity of rejection sampling scales like the condition numbers, the power of D. And in this case, the condition number is something like 1 plus eta for 1 plus eta, basically. So then we choose eta to be small. Eta will be on the order of 1 over D times smoothness. So then,
so in practice, we have something else.
Yeah, so this is the outer complexity, and the inner complexity will be running rejection sampling. And what we can show is that the expected number of queries is a constant before success for eta, which is small enough. Yeah. Yeah. Thank you. Okay, so that was one quick detour to Langevin dynamics, and but so there we see that score is important for sampling, but there we assume that we know the score function for the Langevin Langevin. But now for diffusion model, we want to learn the score function. and in the end, we'll see why. So, right, so this is the problem again. We have IID samples, and we want to estimate the score function, right? And so what we will what we will see is that first, we'll see a minimax rate under an error loss, which is this L2 loss weighted by the target distribution, and also how that implies for the diffusion model. So what kind of class do we care about? So the minimax rate will hold for this class of smooth and subgaussian distribution. So this curly P ML is the class of distributions for that has smooth density, which means that the score function is Lipschitz, or equivalently, the Hessian of the log density, which is Hessian of F, is has bounded eigenvalues. Also later, I'll mention a result about Holder continuity. And so we say that the distribution rho is Holder smooth with this parameter beta if the score function is the difference is bounded by the difference of the points that has this beta factor here. So when beta is 1, this is the Lipschitz case. And recall that we say rho is subgaussian if this moment generating function is bounded by something that scales quadratically with the vector here. Right? So for example, a Gaussian distribution is in this class where the subgaussian constant here is the scales like the maximum eigenvalue, and the smoothness scales like 1 over the minimum eigenvalues. Right? But this class is much more general because subgaussianity just imposes tail behavior, basically, right? So we don't assume convexity or anything like that. And this is the loss function that we care about. If we have a score estimator S hat, then we define the score, the error of S hat with respect to this unknown distribution rho as this quantity, which is the expectation under the unknown distribution of the L2 distance between the true score and the estimator. Right? Why this one? Because this is what is needed in diffusion model. And one thing to note is that if S hat is a proper estimator, which means that it is actually the gradient of some log density, the score of some density estimator, then this loss function is equal to the relative Fisher information, right? So if we recall that in classical statistics, there's been a lot of work on classical density estimation. Given samples, we want to estimate the density. And there, usually the results are stated in terms of error in L2 over the whole space. So not weighted by the unknown distribution, or in something that, like Hellinger distance. So then in this view, we can view this score estimation as like density estimation, but the score, the error function is different, it's like this Fisher information, right? So how does this relate to other quantities? Usually Fisher information is larger, right? Because recall that log says that Fisher information is an upper bound to KL, and Poincare, for example, says that Fisher information is upper bound to TV squared, and TV squared and Hellinger are comparable, right? They are sandwiched between each other. So typically this Fisher information is a larger quantity, but here we want to basically reverse this inequality. We want to get an upper bound to this error loss. Okay, so for the upper bound, what is the estimator that we study? And so this is where in practice for diffusion model especially, there has been a lot of work on using neural network or trying to learn good sophisticated estimator. Here we try to study what is the simplest estimator that we can look at. Well, it's something that's formed by kernel density estimation. Right? So, so from the n IID samples, let's form mixture of Gaussians centered at the observed samples with some bandwidth h. Right? So we take the empirical distribution and then we smooth a little bit with the Gaussian. Then in principle, this is a good estimator for some smooth version of rho star. And in principle, we can try to take the score function of this one. But instead, we will regularize it a little bit. So the estimator that we study is the following regularized score estimator. That so we take the gradient of this density and then divided by the maximum of the density, comma epsilon for some parameter epsilon. If epsilon is 0, then this is the true score function. But this epsilon just makes it so that if the density is small enough, then we lift it up to epsilon. So this is explicit. Given the samples, we can compute what is this quantity for every x in time that scales with n and d if done naively. And I'll mention why we need this regularization. It's good. Yeah, basically, it helps us prove the result. So here's the result, the first result that we prove. So this is the estimator. So fixed dimension. So we assume dimension is fixed, and then n is growing. Number of samples is growing. Assume that the unknown distribution is subgaussian and smooth. Then with this specific choice of epsilon, the regularization parameter here, and h, the bandwidth here. And for n large enough, this loss of this estimator in expectation, since expectation is over the samples from rho star, is bounded by problem parameters times the dominant term is this one, which is n, number of samples to the power of -2 over d plus 4, where d is dimension. Right. So this shows that this is the typical curse of dimensionality, right? That right. So okay. Right. Which means that if we want to make this less than epsilon, then we need n to be something like 1 over epsilon to the d. Right. So let's see. Maybe I will not go through all the proof, but I'll just sketch the proof. But I need to stop here for a second and see if there are any questions. Okay, let me try to sketch the proof because it's actually very simple. So first, so this is the error that we want to bound, and just by definition, is expected value of this L2 loss of the two vector fields weighted by this rho star, the unknown distribution. It turns out that the computation will be much easier if we can replace this rho star by the smooth version. This is rho star convolved with Gaussian with this h. And to do that, we prove this change of measure lemma, which says that if you start from a smooth distribution, you smooth it out a little bit more, convolved with Gaussian with variance h, then the convolved distribution will have lighter tails, right? It goes to 0 faster, but it cannot be too small, right? So this convolved distribution must be at least the previous one divided by this constant factor here. And if h, the smoothing is small, then we can make this small, like 2, for example. Right? Yeah, I'll skip this remarks. And then basically what we did is we decompose this error. So this is the error between the true score and this regularized empirical score estimator. First, we compare this empirical version with the regularized score estimator of the true distribution, smooth a little bit. That will be this first error term. And then we want to control the effect of this regularization epsilon. So we want to compare this distance. So I want to bound this distance. This is the case when epsilon is 0. And then finally, we want to control the effect of the smoothing operation. Right? And for each one, so the first error term was the one that's the most delicate for us. And it follows by combining two main ideas. That follows by the regularization and also by showing a new bound in the Hellinger convergence. So the regularization, the first part is where we really need the regularization. Because essentially, it turns out that regularizing the score function allows us to bound this L2 error, which looks like feature information, upper bounded by something that involves the Hellinger distance. Right. So this is something that that we borrow from the literature of empirical base, because this was also the key result that implied a few breakthroughs in that area, and this was some adaptation from that. So what it says is that if we look at two distributions, rho star h with this score s star h, and another distribution, this rho hat sub h with this score function s hat sub h, then this difference, if we regularize them by epsilon parameter, can be bounded by Hellinger distance. We pay this 1 over h penalty, and then basically just log 1 over epsilon. Right, so regularizing with parameter epsilon only only incurs this log 1 of epsilon factor. But then this is great because, previously we saw that Fisher information is an upper bound to KL or PV or Hellinger and so on. But now this metal, okay, it's actually also upper bounded by Hellinger. So then we just need to control this convergence. So now this just becomes question of given empirical samples, we form this smooth empirical, and we control the convergence between that smooth empirical and the true smooth distribution. And this is actually a classical problem. The previous results that we found in the literature did not assume smoothness. And the result that I get was something on the order of 1/√n times bandwidth to the d/2. This was from the paper by Goldfeld et al. And what we needed to get the matching rate was something that is fairly better. And so it turns out that we could prove the following lemma, which says that now if we also assume smoothness and for small enough step size, then in expectation, this Hellinger distance is going to 0 at a rate of 1/n times h to the d/2, right? And this is also where the smoothing really helps, because without smoothing, we know that typically the empirical distribution converges to the population at a rate that has curves of dimensionality. So that's 1/n to the 1 dimension typically. So we thought that if we smooth a little bit, then we get this 1/n rate, but we pay with this bandwidth, not 1/h to the d/2. So, and then in the end, we need to balance all of them. So yeah, so the first, combining the two ingredients gives us this first main lemma for the error term. So that gives us this bound here. So some problem parameter, but basically depends on 1/n to this times h, and then there is log 1/epsilon also here. And then the second error term is controlling the regularization. So the difference between putting epsilon here and not putting epsilon. And so this is similar to what also appeared in previous works. For various reasons, we needed to reprove a version that's more convenient for us. But basically, the effect of regularizing, we only pay this quantity. So there is an epsilon here. So this is small for small epsilon. And so this scales like 1/h, and then there is 1/h times n squared here. So this part is standard. And then finally, for the third one, we control the error in the score function from smoothing. So if we smooth the distribution a little bit, what is the difference of the score function? And this has come up in a lot of previous papers. And what is known is that if the distribution is smooth, so the score function is Lipschitz, and for small h, then we can bound this error by something that scales with h times dimension. And it turns out that more generally, for any Hölder continuous function, if the score is Hölder continuous for beta between 0 and 1, then we can also show that this score error is bounded by this bandwidth times dimension to the power of beta. So when beta is 1, it goes back to that case. Right? Okay, and then the final error, the final guarantee just follows by plugging in each one of these error terms. I'm simplifying some terms here. And then we want to remove epsilon. The epsilon dependence is really just this log 1 of epsilon. So we can choose epsilon aggressively. So 1/n squared, let's say. And then basically this term disappears, this term disappears. And we just want to balance this quantity with this quantity. So then balancing this gives us this rate, which is n to the -2/d+4. Right. So this gives the upper bound for the Lipschitz score function. And let me just briefly mention that by exactly the same argument, it extends to the case when the score is Hölder continuous. And yeah, there are just like some various places where beta appears. And if you plug in beta equal to 1, this recovers the previous result. So yeah, but we only know how to do this for beta up to 1. And right, so in this case, so basically the upper bound becomes n to the -2/d+4. And then it turns out that we can also prove a matching minimax lower bound, which says that in the worst case, this expected error also cannot be lower than this n to the minus 2 over d plus 4. So up to log factor, this matches the upper bound, and this really shows that there is this curse of dimensionality. And the proof is pretty standard. We extend this difficult function construction, and then use finance inequality. So, okay, so that was the result for the minimax score estimation, and this was for a static score estimation. We have one distribution rho star, and we want to estimate the score function of that. So now, and recall that the loss, the error scales like that. Now, let's see how we can apply that to diffusion model. So, okay, so I'm in the room of experts here, so like I won't go too detailed about this, but basically, diffusion model is something that I find very curious, very strange, very beautiful, very interesting. That basically says that suppose you want to sample from some target distribution nu, right? Langevin would say that let's run Langevin dynamics gradient flow toward nu. Instead, diffusion model says that, well, let's push this target hypothetically to the Gaussian distribution by following the OU process, which is Langevin with Gaussian target, right? So we know that this converges very fast to this one. So like this n should really be here, but this is very small. Oh yeah, no, this is very small because this distance here is exponentially small in terms of this error here is small compared to the true distance, to the original distance here, right? And then, so let's suppose we run this until some time capital T, and then we look at the time reverse process, which is this YT. Then we can show that YT follows this SDE, which for now let's call it reverse OU. And what's nice is that if we can actually run this from starting distribution mu0, which is the same as mu t exactly, then by definition, by construction, we get something that's exactly the original target. Mu t is the same as the target, right? But the issue is that, well, this requires knowing the score function on the forward process and requires knowing what is this mu t here, which we don't know, right? So instead, the proposal is let's run this backward process from Gaussian initial. And so suppose, so this is the algorithm. So run the same channel, but from initial random variable y0 with this distribution, which is Gaussian. So run the same channel, assume we can do that to get some output rho t star. And then just by simple calculation, this is still a very good output because the KL divergence of the target is going to zero exponentially fast with t, with no dependence on any problem parameter. This is determines 2t here, right? And maybe let me just step through why this is true, because this is what we want to show, and by definition, this mu is the same as this mu sub t. So then really the key step here is that the KL divergence between this output must be at most the KL divergence of the inputs, and these are the inputs to the same reverse OU channel, right? And this is the data processing inequality for this reverse OU. And then by definition, all of these quantities are just KL divergence between the Gaussian and this output mu sub t. But then now we know that this is the output of the forward OU process, and we know that this is bounded by this exponential factor times something that only depends on the problem on the target nu, right? The distance, the KL divergence between the target and this Gaussian here. So I find this very amazing because we can get exponential convergence rate with uniform rate just by exploiting the fast convergence of the OU process, right? Whereas previously for Langevin, we get e to the minus 2 alpha t, where alpha is the, say, the log Sobolev constant for this mu, right? But then, of course, to actually implement this in practice, we need to simulate this reverse OU process, right? So for that, first, well, there can be multiple ways of doing this, but typically we replace this score function by some score estimator, and then we discretize time to simulate the SDE. And if we do that, then we get this algorithm, which is called, well, various names, but this one is called the DDPM. And yeah, well, this is the formula for this iterate YK. And really, this just comes from integrating this SDE. If we replace this by an estimator, and then we make it a constant along each small time interval, and then integrating the result, and then that's how we get this e to the eta and so on. But basically, we have some discrete time algorithm with step size eta, and number of iterations is capital K, which is T over eta. And then the question is, how well does this sample from the target, right, given the discretization error and the square estimator error? And recently, there's been a lot of very nice, very beautiful work, including one by Sitan Chen and Sinho Chui et al. That says that really sampling, in a sense, is as easy as learning the score function, because assume that, for now, assume that the score function is Lipschitz at all time, and time at the step size is small. And crucially, assume that we have good score estimator as head, which means that this loss function, this is the L2 loss weighted by this unknown distribution mu sub t, in expectation is less than this sum constant epsilon squared. Then under proper choices of, no, just under these conditions, then in the end, the algorithm will output a sample with this distribution rho sub t that has TV distance bounded by something that goes to 0 exponentially fast with constant with uniform rate here. So this looks like the ideal reverse OU case. But then this is the part that comes from discretization error and then the score estimation error. Right? I'm simplifying the result a little bit here, but basically these are the two error terms that come up. So and then these error terms still scale with this square root t time. So the turns out this is enough to get iteration complexity, because if we want to get error less than epsilon, for example, in TV distance, then from the previous bound, turns out that it's enough to choose t basically log 1 over epsilon. Step size eta needs to be small, epsilon squared, and we need to get the score estimator to get error less than epsilon. So if we want small error, then we also need a very good score estimator, right? But the result says that under these parameters, then it's enough to run the DDPM algorithm for this number of iterations, which is dl squared over epsilon squared. And what you notice here is that, recall that for the basic ULA, for the unadjusted Langevin algorithm, even assuming log Sobolev or strong log concavity, for example, in discrete time, the iteration complexity was something that scales like dimension L squared smoothness over epsilon squared. And then there is this 1 over m squared here, which is the log Sobolev constant. But for many applications, for many problems, this log Sobolev constant can be very, very small. So then if we run ULA, then this becomes a very large quantity. Whereas for DDPM, we don't have dependence on m here. We don't have dependence on the log Sobolev. But we do assume that we have good score estimator. Right, so then the remaining question for this diffusion model framework is, how do we find a good score estimator with this guarantee? Basically, and how many samples do we need? So then let's just apply our previous result. Right? So this says that, so now assume that we have samples from the original target, which is mu at time 0. We want to estimate the score at time t along the OU process. We know that at time t, the solution to OU looks like some rescaled version plus Gaussian. So from the samples, let's form this mixture of Gaussian. This will be an estimator to this true distribution. And then let's take the score function of this one and regularize it a little bit. Right, so this looks exactly like before. One difference is that previously for the static estimation, the smoothing was something that we added just to make the rate work. Here, the smoothing t actually comes from the problem, right? Because we get samples from time 0, and we want to estimate scores from distributions at time t in the future, which involves some smoothing. So the smoothing comes sort of like for free for us. And then by applying the same argument, what we can show is the following, that suppose the target distribution is subgaussian with Lipschitz score function. Then choosing this explicit epsilon, 1 over n squared for the regularization. For any t which is bigger than, say, eta, this expected loss scales as something that goes like this. And basically, for small t and eta, this error here scales like 1 over t times n from here. And then there is this 1 over eta to the d over 2 from here for small eta. And then this means that if we want to make this error less than epsilon for all t, which is bigger than eta, then it suffices to have this many samples. So this scales as 1 over epsilon squared, this is the desired error, but scales with this eta, 1 over eta the d over 2 plus 1. Eta is a step size in the algorithm in the end. And then combining with the convergence result, this is the guarantee that under the same setup as before, to get error less than epsilon, we need this many samples. So something that scales, d is a constant here, but still like d to the d over 2. And then there is 1 over epsilon to the d plus 4. So still something that grows exponentially fast and probably not the right rate to explain what happens in practice. So so in this work, we studied the problem score estimation from samples, and we showed that there is this minimax rate. For quite a general function class, like subgaussian and smooth Lipschitz store. And the upper bound is very explicit, very simple. And this implies a sample complexity for diffusion model, which is still not optimal. But then I think there are a lot of interesting questions because it would be very interesting to get minimax rate in stronger norm, not just in L2, but in L4, LP, in moment generating function, for example, because there can be other applications of that result. Also for other classes of distributions, not subgaussian, but what if it's log Sobolev or like other classes? I should mention that there have also been a lot of, a few related work, concurrent work that study similar questions, but they assume different conditions, like the distribution is in Sobolev class or Besov class and so on. So there can be a lot of different variations here. But I think more interestingly, what can we say about real score estimation with neural network? I think that's all I have. I have some backup slides, but thank you so much and happy to answer any questions.
Do we have any questions?
So for this, I mean, this empirical score, just a very empirical question. This is not about your. There is this empirical thing that if you use this kind of score estimator, you memorize the data as you go back and sample using this sort of estimators. Is there any way to understand this theoretically? I mean, I guess maybe it's trivial intuitively, but.
Yeah, no, I think that's a very interesting question. So the question was, if we just use the empirical score estimator, then we might expect memorization effect. So here we actually regularize a little bit. So this regularization makes so that it's not exactly the empirical score. So this might help generalization. We didn't study that question exactly, but that's an interesting question that there can be different ways to formalize how to do this. But but for this work, we think that this epsilon is helping us to avoid that memorization.
I have more questions.
Something that's sort of come up in using neural networks to approximate functions and these sorts of things, that the sort of ability to approximate function, if you just look at like standard function classes, like smoothness or that sort of thing, then the neural networks in general don't really outperform just polynomial things. And I guess that's also kind of what's going on here, where you're just using a Gaussian mixture to compare to what's traditionally being approximated with a neural network. And but might there be some special classes of functions, and maybe something like Barron spaces, what came up with the function approximation, that might be scores that are better approximated by the types of neural networks used for diffusion models, and what's the distributions those to compare arise from?
Yeah, no, thank you. That's a very interesting question. Yeah, so here we only look at Gaussian kernel, partly because the computation involves a lot of this Gaussian smoothing lemma and so on, which is very nice. Yeah, but even yeah, so the answer is like, I don't know, that would be very interesting. It would be interesting to understand if we use other kernel functions here, can we prove currencies for other distribution classes? Yeah, but I think that would be very interesting. What is the class of distributions whose scores are well approximated by neural networks? That's what we're asking, right? Yeah, I don't know, but I think there might be some recent papers along that question. But yeah, but happy to discuss more. Thanks.
Do we have more questions? Probably I have one question. So previously you described the result that for Lipschitz case, you have some rate, and for the Holder case, and the rate is reduced somehow.
The rates are the same. So yeah, so this is the so if we ignore all of this, basically the rate looks like this, and if you plug in beta equal to 1, which is the Lipschitz score case, we get n to the minus 2 over d plus 4.
Yeah, probably the previous one. I think.
This is the Lipschitz. Yes, so the rate was n to the minus 2 over d plus 4.
I think there's probably some intermediate result. I'm just
Oh yeah.
curious.
Yes.
Here,
Yeah.
So here we have this beta is just from the Holder continuous, this Holder exponent. So that
Yes.
we have this type of, and this restriction for h is the same.
No, yeah. Interestingly, so this result actually holds for all h. Yeah. So this result we proved via different technique, which was probably unnecessarily complicated. So that's where this comes from. But this one we proved via different technique that actually holds for all h. So in fact we can also remove this.
Okay, so you can use the same technique to prove the Lipschitz.
Yes. The second technique we arrived at sort of like later after we finished this one. But yeah. But yeah, like it would be interesting to understand, like the proof here was somehow more complicated than needed.
I see. Thank you. If there are no more questions, let us thank Andre again.